we're going to start with this video, this little activity to get us thinking about circles to start with, and then we'll talk about it. Okay, sorry, I'll use this. All right. Hey. I don't know what's doing. Please stop. We're just going to start the video here. All right, so you have this person. They're typing on their computer. What time is the Texas football game? All right, and they look it up, and it says Saturday, December 5th at 11 a.m. Okay, so they're going to go download the ESPN app to watch it on, but it's 10:59. They're kind of close. So they're downloading it. Okay, hit install. Start downloading. And our question that we want to determine is, will this have enough time to download before? Yeah, so they're hitting that download button at 11:59. Do they have enough time? Do they have enough time to download it? So that is your question. On the front of your page, it should say official guess. So you can guess either yes or no on whether you think they will have enough time to get it downloaded and get started watching at 11, or if you don't think it will download by 11 a.m. what now? So put your guess down, and then think: what are some things you noticed about this situation? So what are some things you picked up? What are some things that are important? So just get your thoughts on that. So based off this video, based off this situation, do you think yes or no? And what are some things you noticed about it, or wonder? What are some questions you might have? Give you a moment to do that. So, official guess, yes or no? What are we thinking? Everyone's on no?
I'm on yes.
Everyone's on this? Okay, it's cool. You can do either way. So majority knows, some yeses. What did we notice, or what are some things we caught on? Amanda. It took 14 seconds to get a certain length in, a little bit far in. Okay. What else? What was it? It's a... Oh, okay, so like the downloading things in ARC. Good. We'll talk about ARC. That was important.
So like
dealing with circles.
Did they start downloading it right when it turned 11?
Yeah, we're going to say right when it turned 10:59 to hit that down. Just for the sake of convenience, keep it easy for us. We're also going to assume it doesn't have any buffering or anything like that. It's going to download at the same speed the whole time. So we'll assume it's consistent. It has a constant speed, just to make it easier on us because we can't assume it's going to buffer.
So the thing was like 14 seconds and it looked like it wasn't a quarter of the way. And then on top of that, you don't like if you get like an app, you have to like sign in and all that kind of
Right.
stuff.
We won't worry about signing in or anything like that. We just want, is that app going to download
No.
in a minute? So, all right. So you said at about 14 seconds, it looked roughly a quarter away, or just about a quarter away? Under a quarter?
Yeah,
Okay.
yeah. Well, yeah, it was going to be like 15.
Okay, so what are some pieces of information that would be helpful in us for us to actually be able to solve this?
To like double that length to be 28 seconds.
So you know to double that length would be 28 seconds. Okay. What were you saying, Morgan?
The size of the circle, like how big circumference.
360.
Okay, so the circumference of the circle? That's not. So if we knew the circumference, that would be important. Okay, that could help us. What are some other things that might help us if we knew them? The length of the arc? Okay. Length of the arc. Any other thoughts? Those are two, yeah, given those two things, we could probably figure it out. Take this, just a screenshot at a random point on the thing. At 4 seconds, it was this long. Based off of this, you think it's 1%? You have no idea? You want the circumference of the circle and then the length of this to help
Does
to
square have anything to do with it?
The square is just, we're gonna say the square is like the center of the circle. This is your center point. It's just, I don't know, the symbol they have, side, zero, half.
You just want to pause it. Yeah.
Could we cut it into quarters?
Like full quarters, like a fourth each? You could.
But that would be how.
Yeah, so can you do like the whole radius thing? Yeah.
One thing we could do on that same idea of cutting it into quarters is if we determine how much of our circle this piece is,
We can figure out.
we can figure out how many of those should fit in. And if each of those is going to be 4 seconds, that should help us determine it. So what could we use in order to determine how much of that circle this is?
Protractor.
Protractor, what would you use a protractor for?
The
Measure the
angle.
angle.
Measure the angle. So if we find this angle measure,
Because the angle.
Because then it's whatever it
Angle of
is,
the circle 360.
the 360.
Okay.
Divided by.
so we know the whole thing has to be 360. So we find that little piece, we know we can figure out how many pieces fall under 360. Okay. So you could bust out your protractor or you could use some other thing. I use Desmos, and roughly looking at it and using these lines, we're able to determine that it's a 20-degree angle. All of them. So 4 seconds happens within 20 degrees. So given that information, knowing that it takes, so 4 seconds is 20 degrees of change, use that information, see if you can determine, okay, how long is it actually going to take to get the full circle? Will there be enough time? So take a moment to see. All right, so someone walk me through the steps on what they did for this problem. Alex.
So we had like your 360, the total angle of the total circle, divided by 20, which is how many like degrees each of like the little thingies are.
Okay.
And I got 18. And so then I did like 18 of those like little pieces, thingies, each one was 4 seconds, multiplied by 4. And I got 72. 72 seconds is minute and 12.
Good. So we knew it was 20 seconds for that 4 second piece. So we were able to take 360, the full circle, divided by 20, which gave us 18 of those pieces. We know each of those pieces has to be 4 seconds long, so we multiplied that by 4, which gave us 72 seconds all the way around our circle. So would it work? No. So they're probably going to miss kickoff or whatever. I don't know. It doesn't matter.
Going into national anthem.
Yeah, national anthem, which is important.
They're going to miss like 5 seconds.
So I initially had a video that showed the answer, that showed it going to 72 seconds, but I didn't link it, so I'm sorry. But 72 seconds is correct. You got the right answer. Good job. I just don't have the video that shows you got it right. Okay. So let's talk about why we did this and what are some important things that we learned from this situation. So big idea number one is that there is a constant proportion or a constant proportional relationship between the angle and the arc measure on our circle. So that angle in there and the measure of that arc, there is a relationship between these two. The wider the angle or the larger the angle should be the larger the arc and the larger the measurement of the arc. And so if you have two circles that are the same with two different angles, you can determine what both those arcs are as long as you know what one is. The word proportion, when have we seen the word proportion in the past?
I don't know arc ratios.
So the word arc is the length on the outside of that circle that's encompassed within that angle. So this is an arc. And we'll talk about what are some different types of arcs.
Like the colors arc that we do last year.
Not that.
That one.
But what is the word? When have we talked about the word proportion in the past? Ratios. Yeah, a proportion is a ratio. So a proportion was set up by having two fractions and saying them equal to each other. And so we could create two fractions from a situation, and we could solve for that missing thing by crossing multiplying. The most common time we did this was when we were dealing with similar triangles. We knew similar triangles have proportional side lengths, and so we were able to solve for the missing triangle by knowing what that proportion was, as long as we knew, like, okay, what is the length of this side compared to the length of this side? So this side, what's the we can do that same idea using our arc measure and the angle. So we know that 25 feet is related to, or takes 90 seconds, or sorry, not 90 seconds, like a 90-degree angle measures to 25 feet with this specific circle. So if we know what 120, if we have a 120-degree angle, we should easily be able to figure out what is that missing measurement based off of our proportions. What would we have to do from there? Catalog press cross multiply. So we can do 25 feet times 120 degrees and 90 degrees times x. So 25 times 120, that gives us 3,000. And then 90 times x is 90x. Last step is just to divide to get x by itself. And we should get x to equal, yeah, 33.3 repeating. So 33 and a third foot. That would be your measurement of that 120-degree arc. Yeah, so if you have a repeating number, you can just put a line above it to say it's going to be 3. I really just had to put 1 3 and just put a line over it above it. 2. So good. So we can determine what that arc measure is as long as we know what those, or as long as we can use those proportions, as long as we have some information to work with, we can read those proportions. And so based off of that information, we can go into the second big idea. So how are we able to determine that triangles were similar? What do we have to look at? We had
They're side lengths because those are different, but they're the same.
They would be like proportions, and we would be like multiples of each other.
so similar shapes have proportional side lengths and same angles. So proportional side lengths and same angles. So they weren't the same size, but they had they were the same shape. They all looked that they had the same shape. So as long as we had two angles that were the same, by angle similarity, we were able to say those triangles were similar. So these are similar by angle similarity. And then we were able to say that the sides are proportion. Now let's think about circles. How can we show that all circles, every circle that you ever run into, is similar to every other circle? What's unique about circles compared to triangles? It has no sides.
Isn't like something with them will always be the same for every circle? I don't remember what it was.
And all circles should be
Isn't it like the length of
So every circle has a radius.
it would put something in every circle.
If I change the radius on a circle, so like I have these two circles, so I have this radius, my little r in there, and then I have this circle, this radius.
Isn't like something times 2 or divided by 2 or it was something like that.
So radius times 2 is your diameter.
Yeah.
Are those both circles? Do they both look like circles, like a circle should? Have you ever seen a circle that doesn't look like that type of circle?
It's not a circle.
Yeah, it's an oval or some other shape.
So in order to be a circle, it has to be, you have to have a center, and then every point on that circle has to be the same distance. That's like your definition of a circle. And so if you have any other shape that doesn't meet that definition, it's not a circle. So the only thing that can change about a circle, the only thing that really makes a difference is how long is that radius. But other than that, that's just a proportion. So all the angles, if we think about angles of a circle, they're all the same. The only thing that's different is the side lengths or the size. And so by thinking about similarities, our angles are the same. The only difference is the side length. The only thing different about circles is that the radius is different. And so that makes every circle similar to each other just because the only thing that's changing is the radius. It's like a dilation. We thought of similarities or similar triangles as dilations. Every circle is just another dilation of itself. It's just determining how long that radius is going to be. Because you can't change what a shape of a circle is. It's a circle. It's like axiomatic. Like where we talk about those triangles and bracket. Are we okay with this? All right. We're now going to move into arcs. We're going to talk about arcs. So we have two types of arcs, major and minor arcs. And we're going to talk about how we can determine arcs and how we can use these to look at angles within circles. All right, so to start off with, at the top of your paper, it should give you 3 examples. 2 of them are central angles and 1 of them is not. So based off these examples, what would you assume is the definition of a central angle? What does it mean to be a central angle? Yeah, that's it. So both of these ones with a central angle, that vertex is in the center. The one that isn't a central angle, the vertex isn't in the center. So the vertex of the angle, if I can spell words, the vertex of the angle is in the center of. Now, when we use the word center, we mean the direct center of that circle, not just in the middle of the circle or inside the circle, but it needs to be directly in the center of the circle. So this is an angle that's in my circle, and the vertex is inside, but it's not in the center of my circle. There's only one specific center of the circle. Okay. Okay. So with central angles, when you have an angle like this, you get a couple of arcs that form. So we have one arc inside the angle and one arc outside the angle. So we call these our major and minor arcs. Now, looking at these 2 examples of major and minor arcs, what are some things you notice about them? So your minor arc is going to be smaller than your major arc. So together they'll have to equal 360 degrees. So good, that's something we'll want to write down. So together.
So like the word for that,
For 360? Not that I'm aware of. We have like complementary 90, supplementary 2 angles added equal 150, but we don't really have to make 360 about it. So major and minor arcs. So together they have to equal the whole circle. Together they have to form a whole circle. So together they'll have to equal 360 degrees. What else do you notice? The central angle, what about it? What do you know about the What do you notice about the measurements of the arcs and the measurements of the central angle? So your minor arc is equivalent to that measurement of your angle. So we'll put it this way: the angle measure equals the arc measure. So whatever that central angle is, it's going to be equivalent to whatever that arc encompassed in it is. So if you have an angle of 60 degrees, that minor arc degree is 60. If you have an angle of 179, that means the arc is 179 degrees. Now that's not the length of the arc. It's not 60 feet or 179 inches. It's not necessarily a length. It's a measurement of an angle. Are we okay with this? So what is the measure of the major and minor arc for each of the following circles? So we have a couple circles. We want to figure out what's the measure of my major arc and what's the measure of my minor arc based on this situation. So for the first one, what is my major and minor arc? 310 for which one? Your major or minor? The 310 will be my major arc. My minor arc. Good. So just from that central angle, I know it's 50, and then 50 minus for 360 minus 50 has to be 350. So using that information, take a moment, see if you can solve for the other 2 major and minor arcs in this situation. What did we find for our major and minor arc of our middle circle? minor is 110, and the major is 250. That's not. Good. And the last one, major and minor.
Major's 200, minor 150.
So your major you would given to you of 200, and your minor arc is 160. And you know that central angle would also be 160 as well. Good. Pretty simple, pretty easy. We know it's just got to equal to 360 degrees, so it's just adding. So we're going to take this just a little bit one step farther, throwing in a little bit more angles and looking at what are the arc measures of all these angles when you start throwing in more than just one. So we have what is the measure of arc, or what is the measure of each arc, and then we know CE is our diameter. So first thing, what is the measure of arc EF?
120.
120. So EF is just right here, but then that's just 120 degrees. What is the measure of mark ECF? So
It sees the diameter when that get over to the directly cut.
let's talk about why some of them have two. Some of them have two of the letters, and some of them have three. So EF, it just has two. We see it right there. ECF means I'm going from E to C, then onward to F. So it's this whole arc on the bottom. The reason I can't just put EF for that one is because if you just saw EF, you think, oh, it's 120 degrees. But by putting that other middle letter in there, you know it has to be this whole, it's this side we're going around to the bottom. So that's why on some of them we have to put three letters just to remind people okay, which one you're actually talking about. Because there are two ways to go around the circle. And so this one would be 240. Good. So we can take 360 minus 120, which gives us 240. We need that off the arc. And the last one we're looking at is CFE. CFE for this arc. What would that one be?
240.
CFE?
Well, isn't it just an upper circle?
So we know because CE is the diameter, it cuts the circle directly in half. The diameter has to pass from one side to the other, cutting it in half. So what would it be then? What is it? It's just half of our circle. So anytime you see a diameter and an angle encompassing a diameter, you know it's always 180 degrees. Good. Those arcs. So same idea for the next one. Same situation or similar situation. You have a couple arcs. You have a couple more measurements to run in this one. See if you can figure out what are the measures of these three arcs. So you have DBE, CED, and CD. Figure out if you can find the measurements of each of those. All right. So what did we find for BE or DBE? Sorry. What was that? 150. Good. So DBE was 150 degrees. What do we find for CED? 210. So CED was 210. Once again, that E's in there just to tell you which side of the circle to go around. And then CD, also 100 CD. It's just left over. So you can take your 360 minus your 210, and that gives you what's left over. Your 150. Awesome. So we just have two other things to look at, and then we'll be good for the day. All right, so I have two circles. Both of them are centered around point A, or center of A. They both have the same center. I have CE is one arc, and BB is another arc. I want to know, are these arcs congruent? Why or why not?
Yes,
Why do you think so, Morgan?
because they share the same angle.
So they both share the same central angle, so that makes both of their arc measures 70 degrees. So in that case, you could say, yes, these are congruent to each other. The angle measure, the arc measures of both those arcs are congruent. Is there a way that's possible for them not to also be congruent?
Yeah.
What-
Radians.
So yeah, both these circles have a different radius, so the length of each circle is different. So you can say, based off, if you're talking about the length of the circle, no, they're not congruent. But if you're talking about the arc measure, yes, they are. So it's kind of a trick question because it could go yes or no. But please, we're talking about arc measures today, so we'll say yes, they are congruent because they both have the same arc measure. If you're talking about lengths, though, you can say no, they aren't congruent based on that. But good. Last thing we're going to talk about, the last little question we're going to look at, is we have this little situation. We have CB being the diameter of our circle. We have the measure of CD, or we want to find what is the measure of CD. So we know that's 4x minus 20, and we have x is dB. How can we go about figuring this out?
Set 4x minus 20 to 20.
So 4x minus 20, you want this equaling 180? Do we agree with this?
Wouldn't you just have to add on whatever x was to 180?
So because this whole thing is diameter, this all has to be half a circle. So we can't just have 4x minus 20. We also need 4x minus 20 plus 180, or plus x, I'm sorry, equals 180. So we want to make sure we include both of those angles in there, like coordinates. And from here, what would you have to do? Do your thing, combine the like terms, simplify your x. So if we combine the like terms, we get 5x minus 20. Inverse your constant, so we would add 20. So you get 5x equals 200. And doing all these things. Get x by itself by dividing by 5. Divide by 5. And we get x equaling 40. So there's two ways you can go about to solve this. You can plug x back into 4x minus 20 to get that whole angle, or you can think, all right, if this one is 40 degrees, that makes this for 180 have to be 140. Left over. You're good. So that's where we'll pause it for today. We'll continue talking about parts a little bit more tomorrow, and we'll talk about constructions on Wednesday.